Hello, this is going to be a combined chapter from chapter 17 and 18. We're running out of time, so we're sort of taking snippets from both. So they're not complete chapters, but just the highlights. First thing we want to talk about, this part's from chapter 17, and we're talking about carboxylic acid derivatives. And one of the things you just have to remember about carboxylic acid is that not all carboxylic acids are equal in acidity. Okay. So you can actually change the acidity of a carboxylic acid by putting electronegative groups near it. So the more electronegative group, the more acidic. So if you had something like just plain acetic acid, the pKa is about it's like 4.5, stuff like that. So, but if you put a chlorine on here, it increases to 2.8. Put a fluorine on here, right next to this carboxylic acid, is 2.6. Now, I put that on there. You have to remember that this is just an abbreviation for this, for the carboxylic acid. Just wanted to give you guys some practice on seeing it. The more electronegative groups, right, the more acidic it is, right? So if you have 3 chlorines, it's 0.7. It's really acidic. As you decrease the number of chlorines, the less acidic it is until you get to the acetic acid here. So the more the merrier here. So also distance makes a difference. So the farther away, say, a chlorine is, the less effect it has. And it has a little bit, even way out here. Instead of the 2.8, it's more like 2.5. But as you move the chlorine closer, it becomes more acidic. So just something to remember. Okay. Now we're going to be talking about these different groups. There's another one in here that's, you'll see it's the sulfur version of an ester. So an R group. An R group is just any sort of carbon group. It doesn't matter. So this is called a thioester. You'll see this pop up from time to time. You'll see it with me as well. But these are typically acid chlorides because they're made from acids. Some of that acid anhydride or just anhydrides. Again, they're made from carboxylic acids, but they're 2 acids put together. Ester is O carbon. So nitrile, we're not going to talk too much about nitriles. And then amides, and it doesn't matter if there are what's hanging off the nitrogen here. If it's just two hydrogens, 1 carbon group, 2 carbon groups, doesn't matter. They're all going to be an amide. Okay, so naming of amides. Okay, now this one actually makes a little bit more sense. Okay, so for let's say it's a very simple amide. So let's say here, so CH2, CH3. Okay, so the main chain is always going to start here. Okay, that's always going to be number 1, and it's always going to go away from the nitrogen. Okay, so here it's with the simple one, there's the main chain here. You could say this then becomes a side chain. Okay, and then all the other side chains you would see. The numbering is nice because this is always going to be number 1, number 2, and so on and so forth. Okay. For the side chains, you would name any side chain you had over here just as normal, but this becomes a side chain as well. Okay, and for that, I should say, for the main chain, right? This is too long, so that would be ethane, right? But we're going to take off the suffix e and then amide too. So it becomes ethanamide. Okay, and so the ethyl group. There's the ethyl group here. There's no other side chains over here. Okay. To indicate that it's hanging off of the nitrogen, we say, we're going to put an N there. If it's hanging off over here, we just put the carbon number that we've got. Okay, so you put this out front, just as normal. The N acts just like every other number, and so it becomes N-ethyl ethanamide. This is a really simple example, but it's actually not that complicated. Okay. So if we had this, one. Okay, you can always put in your dots if you want for carbons. Okay, so since this is going to be carbon 1, we're going to go away from the nitrogen. Oops, no, forgot a carbon. Okay, so we're going to go 1, 2, 3, 4. Don't forget to go to the side chain. 1, 2, 3, 4. Okay, so it doesn't really matter. So we're going to say those are that's the main chain. So it's C4, which would normally be butane, but we're going to take off the E and add amide. So it's butanamide. Now, as far as the side chain goes, we've got this one here, we have a methyl, and then we have this ethyl, and then we have a propyl. Those are two distinct side chains. Okay, it's not a pentyl. It's a ethyl and a propyl. Okay, so for these guys, so the numbering this always starts at 1, 2, 3, 4. Okay, so the methyl is hanging off of carbon 3. The ethyl is hanging off of the N, and the propyl is hanging off of the N. Okay? So you go first alphabetically, right? So we're looking at ethyl, ethyl, propyl. So ethyl goes first, so it's going to be N-ethyl, and then methyl, so 3-methyl, N-propyl, butanamide. Okay, so here's the name. So we have a main chain that's 4 long here. Oh, hey, we have an amide functional group at carbon 1. So hanging off of the nitrogen, we have a propyl and an ethyl, and hanging off of carbon 3, we have a methyl. So there we go. Not too bad. Okay. Now esters are a little weird. And this is sort of a quirk of history in how they originally named them, because they would take a carboxylic acid and an alcohol, mix them together, and so it would be like the ethyl alcohol version of some carboxylic acid. So, and unfortunately the name, nobody ever got around to changing the way we do the naming. Okay, and so for this one, what you're going to do is, just like you have the C double bond O side and the N side for the amide, you're going to have a an O side and a C double bond O side. So on the O side here, this side chain here always goes out front. Always, always, always. Doesn't matter what it is. It could start with the letter Z. Doesn't matter. That goes out. So that goes front. Goes out front. And then the rest of it is named similarly to this. Okay. This is going to be carbon 1, 2, 3, 4, right? So so you'd have butane, right? But for the ending, it'd be usually O8, but sometimes it's easier to just say 8. So butanoate. So this would go. So this is an ethyl group, right? So this would be ethyl butanoate. Sometimes you'll see me do parentheses. You don't have to do that. You can. But if we had, let's say a chlorine here, right, it'd be, well, it'd be 3-chloro. And if let's say we had a chlorine here, right, so it'd be ethyl 4-chloro butanoate. Okay, but this always goes first. Notice how the chloro's out after it. Doesn't matter what this is. This side chain here goes out front. So here we go, right? So we have ethyl. So ethyl butanoate. That's just what we did. Okay, if we want to do something a little bit more complicated, slightly, I guess. Okay, so we have a chlorine here, nitro here. Okay, so this part here, right, that's what's going to go out front, so that's going to be ethyl. The rest of it is going to be 1, 2, 3, 4, 5, 6. Right, so the chloro is hanging off of carbon 4, the nitro is hanging off of carbon 2. Okay, so it's going to be, so this part here, right? Oh, I'm 1, 2, 3, 4, 5, 6. So this would be the main chain hexane, right? Take off the E and add O8. Right? So this part here would be, right, 4-chloro, 2-nitro, hexanoate. Okay? But what you have to do first is put the ethyl up front. So it would be ethyl, 4-chloro, 2-nitro, hexanoate. Okay, it doesn't matter what this is. This goes out front. The rest of this stuff gets named. The rest of it gets named as normal, and then you just stick this group out front. I know I'm harping on this, but it's one of those things. It makes absolutely no sense. Well, sort of, knowing the history, but they never got around to fixing it, so we have to suffer. Now, a lot of these things, okay, the carboxylic acid derivatives, they can go in and they can undergo nucleophilic attack to get a substitution. It's acyl substitution because the acetyl bond O is considered an acyl group. And what happens is that's how all of these are going to work this way. So let's say you had let's say X, I don't know. And then let's say you had an alcohol. Okay. Remember, this is a polar covalent bond here. This group here has lone pairs. Okay. So what's going to happen is that these lone pairs are going to get attracted to that carbon to make a new bond. This carbon now has 5 bonds, can't do that. So the easiest way to get rid of a bond is to push those electrons up here. And so you end up going through what's called the tetrahedral intermediate. Oops, that's a single bond. I don't know. Oops, I forgot to change the colors. Okay, now, what's going to happen is if you have a good leaving group here, what's going to happen is this is going to collapse, and that's going to kick away. Because it wants to reestablish the C double bond O. It's a lot more stable. Okay. Now, as this group is falling away, okay, it's going to come in and it's going to snag the hydrogen to move that back there. And so you're going to end up with CH3, C double bond O, X, CH3, H. Okay, that's how all of them work. Okay, so this is just water coming in. It's going to come in, attack, up, down, kick away, and then, well, in this case, water is going to come back and grab it. But that's beside the point. That's how they all work. Okay? Now, the problem is this. If this group is a carbon, this leaving group here is a carbon or a hydrogen, you do the same reaction. Let's just make this, sorry, I need to think about this for a second. Let's say this is a really big, let's say it's a carbanion here. What you would end up getting is something like this. The problem is, if this were to collapse down, right, you'd have to break a carbon-carbon bond. That's just not going to happen. So what ends up happening is this is stuck as an O-. So when you dump it in when you dump water at the end to quench the reaction, this ends up going to an alcohol. Okay, so if you have, say, if your nucleophile is, say, so if you end up having an aldehyde or a ketone here, stuff like that, you're going to be stuck with the OH. It's not going to be able to collapse back down. So just be wary of that if you're attacking with a hydride or some sort of carbanion. Oh, I'm sorry. If you're attacking an aldehyde or ketone. Okay, now for all the other reactions, okay, you're going to need to know this list. Okay, so acid chlorides are the most reactive, amides are the least. So the order goes acid chloride, anhydride, thioester, ester, amide. Okay, so what this is saying is that chlorine, acid chlorides, can make all of these, the ones below it. Anhydrides can make thioesters, esters, and amides, but they can't make acid chlorides. You can make things that are below you, but you can't make the things that are above you. So thioesters can make esters and amides, but not anhydrides and acid chlorides. And so it wants to go downhill. Okay? And so if you have, so acid chlorides can make all of these. Okay, so it doesn't really matter what you end up making. And so the way these are going to work is that, let's say you have an acid chloride. Okay, you have an amine. Okay, you have a C double bond O. You have something with a lone pair that's going to attack. So this attacks here, pushes the electrons up. They collapse down. You kick away the leaving group. And as this thing is leaving, it snags one of the hydrogens on the nucleophile. Like that. That's how they all work. Again, you're going to form that you're going to kick this up to form the tetrahedral intermediate. That's going to collapse down, kick away your leaving group. The leaving group then comes back and snags a hydrogen. Okay, so for this one, so this is going, right, because you're going to have lone pairs here. So we're going to attack, up, down, kick away. Now what I should have done, plus HSCH3. What I should have done up here is to say, like, okay, this is acid chloride going to an amide. We're going downhill on that list and we're okay. Here we're going from thioester to ester. That's fine. Right? Thioester to ester, that's okay. Now, the other thing I forgot to mention is that you can go side to side. So you can take one acid chloride and make a different, or anhydride, make a different anhydride. You can make an ester and make a different ester, or you can go from ester to carboxylic acid. That's fine too. So that's okay. Something like that. So go ahead and do the reaction and then do a quick check. Okay, so we have plus NH2 or NH3. We have a set of lone pairs. We have a C double bond O. That's going to attack there. Up, down, kick away. And as this is leaving, it's going to snag one of those hydrogens. H2 plus H, like that. Again, we're going to go from an ester to an amide. So we're good. Now for here, because we are, we're not going to talk about this much, I'm going to give you symmetrical anhydrides. but they work the same way. If you're giving anhydrides where the left side is different from the right side, the first one that's going to get attacked is the one that has the is going to be less sterically hindered. Okay? It's going to have a smaller group on this side, but for this one it doesn't matter. Okay, so now again we're going to have the lone pairs come in and attack. I usually do the one left, but that's okay. Attack and kick up, kick down, kick away. Now this whole thing, right? We're snipping the bond there, so this whole thing goes away. And again, as it's leaving, it's going to snatch a hydrogen. Right, so you're going to have that plus like that. This is just your leaving group, right? You're snipping that bond right there, so this all falls away. So there you go. Oh, you're going from an anhydride, right, to a thioester. So you're good. Last one. So okay. Alright, so we have a set of lone pairs. It's going to attack here, up, down, kick away. And again, as this is leaving, it's going to snag that hydrogen. Right. Plus H2N, right, like that. So here we're going to say, okay, so this is an amide. This is an ester. Here's the problem, right? This amide, you'd be going uphill to go from an amide to an ester. Okay, so this reaction wouldn't happen. So it's actually going to be no reaction. What's going on is the amide is actually a better nucleophile than the ester, or than the alcohol. And so even if you were to get this to form, what would happen is the amine would come in and reattack to reform your this amide here, stuff like that. So even if you tried to do it, it would go back the other way. So in fact, there's no reaction. So be careful. Now you could maybe predict it. Lots of times I'll just go ahead and do the reaction and then just check, okay, because it's easy enough to do. Now the question becomes, how do you make the acid chloride? If the acid chloride is at the highest reactivity level, how do you make it? Well, what you do is you add this compound called thionyl chloride. It's SOCl2. Its entire purpose in life is to turn OHs into Cls. That's it. Doesn't matter if it's an alcohol, doesn't matter if it's carboxylic acid. It turns that OH into a Cl. And the way that it does that is the carboxylic acid will react with it to form, and just do a real, collapse down to make this sort of crazy chlorosulfite, which is a really good leaving group. It's so good that even a chloride, which is a pretty crummy nucleophile, can come in and do another substitution. So up, down, kick this thing away to leave the chloride. The other thing that helps is the fact that this compound will actually decompose down to SO2. So go to your stack. It'll smell bad, but it'll go up your stack. So you have to generate these in situ. It's really hard to get those. I don't know so you really can't buy them like this. So you have to generate them and then react with them right away, because they react with just about everything. Okay. Now the next thing. Now this we're talking about is going into chapter 18, and we're talking about, again, we're going to be talking about acidity, but instead of so like OH bonds and esters and things like that, or instead of OH bonds, we're talking about CH bonds. And it turns out, just like the difference between alcohols and carboxylic acids, the presence of a C double bond O adjacent to whatever your hydrogen is going to make a big difference on the acidity. Okay, so if you think about this, right, so if you have CH, if you have ethanol, right, the pKa is like what, 16, something like that. But let me draw it like this. But if instead you had this, right? The pKa is about 4.8. It's a massive drop in pKa, a massive increase in acidity. Same thing happens with this. So if you have a just a regular alkane, right, the pKa is going to be about roughly 44. If it's off of an alkyne, right, it's 25, not too bad. But just popping a C double bond O here changes the acidity of this CH bond by about 24 orders of magnitude. Okay, so it makes it incredibly acidic for a CH bond. And the reason for that is that a base can come in here. You can make the carbanion. Okay, that's generally not good, but it can be resonance stabilized to form the enolate. And so, because you can form this resonance structure, the molecule is okay with this hydrogen going away. Right, you're getting a lot of electrons on the most electronegative atom. That's not too bad. Okay, now enols and enolates. Okay, so even if they're in this form, the enol form, what can happen is they can actually tautomerize, I guess, would be the way to say this. It's not a resonance structure to form the enol and the ketone. The reason for that is because you have a hydrogen that moves. Okay, the hydrogen goes down here, the double bond goes up here. So this is the hybrid of that. But you have this double bond flops down here, but the reason why it's not resonance, the hydrogen moves up there. Okay? Now it turns out that, right, so this is what we call the keto form, which is just the C double bond O form, and then the enol form, right, a double bond and alcohol, right, that ene from the, from alkenes, right, double bond, and the OL for alcohol. So I think it's a portmanteau name. So, okay. Now, for the most part, the molecule is going to want to be in the C double bond form, into the keto form. Okay, the acetaldehyde is almost 100% this. Same with acetone. Cyclohexanone is 99% this. Only a very small amount is going to be in the enol form. The exception for this is the beta-diketones, which we'll talk about later in the chapter. They're kind of quirky, and in fact, they actually want to be in this enol form because you can get this nice hydrogen bonding, which helps stabilize the molecule. But that's a quirk. So a known quirk of these things. Now, the nice thing about these is that you can essentially what you're doing when you have a molecule like this. If you throw an LDA as just a really strong base, it's lithium dimethyl amide. What it can do is it can extract one of the hydrogens next to the C double bond O, okay, to leave behind a stabilized carbanion. Now you've got a carbon with a couple of lone pairs. Now it can go and do SN2 attacks, right? Nucleophilic attacks. So it'll attack here where the leaving group is, and then voila, you've added a 2-carbon piece here. Butyrolactone here, right? You can extract. This will take off one of the hydrogens, leaving the electrons behind. It's just doing what bases do to form the carbanion attack, kick away methyl iodide. So there you go. Okay, you can also react these things with halides. Okay, so after you form the carbanion, you can go in and attack. So this is under basic conditions. Extract this away to form the enol, with that enolate. That can come in and attack a halide, kick away the other one to leave behind the halide on the alpha carbon here next to the C double bond O. It's a nice little reaction. Okay. So if we have this, so remember we're taking away one of these, not this one, not the aldehyde one, it's next door. Okay, so we're going to react this with LDA. Right, that's going to come in attack, move those electrons up here. Now we're going to throw in this compound. It's just a molecule with a good leaving group, so it's going to attack there, kick the bromide away, and so you're going to end up with, I'm going to draw this poorly. You're going to end up with that, plus just Br minus. Okay. Now for this one, right? So here's the hydrogens here. Right? We can't pull off any hydrogens on this side because there aren't any hydrogens. Right? So we throw in our LDA. Right? That's going to come in and grab one of these, put the electrons there, onto that carbon. Okay. And in the presence of iodine, right, just like it did here, this is going to attack, kick away. So what you're going to be left with is you're going to stick an iodine next to the C double bond O. That. Now, when you get to the point where you actually have two C double bond O's next to it, it becomes even more acidic. So these beta-diketones. So so having one C double bond O is good. Having two is even better. Okay, so it's not that this is double, right? It's actually more like a billionfold more acidic than this. Okay, and again, because you can do multiple resonance structures, right? You can put the lone pair here, or you can put the lone pair over here. So with that here or here. So it makes it even better. Now the nice thing about this is that what you can do is, this is really simple to lop this off, just sodium methoxide here. So it's going to attack, kick away to leave this. Now the nice thing is, right, there's still a hydrogen here. Okay, so you can do this again. And so you can actually have two different groups right next to that. So if you go down here, so if you have ethyl acetoacetate, ethyl, okay? Remember there's two hydrogens here. And so if you use just something as simple as sodium methoxide, right, this is going to come in, grab this, put those electrons up there, and you're going to make so hydrogen and then ethyl. Right? But if we do this again, right, sodium methoxide, right, so this would be plus ethanol. CH2, CH3, right, from there. Right, so again, this is going to grab that. Those electrons go up there under that carbon. And so again, you're going to have electrons there, so CH2, CH3, right, plus the ethanol. So if we attach, now in this case, right, so CH3 Br, right, same thing happened before. This is going to attack here, kick away where the good leaving group is, and so now, right, we've made two different carbon-carbon bonds. Right? That's why we're doing this, because it's easy to make carbon-carbon bonds. Okay, not too bad, right? So, now, yep. So that's where we end up with. Now, what we can do is we can actually get rid of this this, what is it, the ester group here. Okay, and what we end up doing is we throw in sodium hydroxide. That makes it into a carboxylate. Okay, you acidify it to turn it into carboxylic acid, and then you heat the snot out of it. And what happens is that this goes away as CO2, and so what you end up with is just that, the methyl ketone. So again, if we go through this process where we add the carbon group and then we do heat, base, acid, and then heat, you end up getting rid of the ester group there. So you would end up with this. So if we did the same thing and we did that process where we said, okay, we're going to do sodium hydroxide and then acid and heat, what we're going to do is just getting rid of that. And so we'd end up with, if you want to draw it like this, that's fine. Okay, it just gets rid of the ester there. So you'd end up with this. If you want to get fancy and redraw it, it would look like that. Okay? Now, malonic esters, it's the exact same synthesis, exact same thing, except you have, instead of a methyl group here, you have a ketone, or you have an O-ethyl. So you have an ester. So in a ketone, you have an ester. But the process is going to be exactly the same. You pop off the hydrogen, right, with sodium methoxide. You add carbon with leaving group, and then you attack. Now, when you go through that same process of adding base and then acid and heat, what ends up happening is not only do you get this removing of the ester, doesn't matter which one, but the other one, because of this first step, turns into a carboxylic acid. So what you end up with is a carboxylic acid at the end. Okay, so this one right here, before you would end up with an O-methyl, or with a methyl ketone, now you end up with an OH group there. Okay. So again, if you wanted to do this, you could add these two groups. You do, after the base and acid heat step, you'd end up removing one of these. It doesn't matter which one. It doesn't matter which one. Removing the ester group and turning the O-ethyl into an OH on the other one. So if we wanted to design a synthesis for this, okay, what we would need to do is O-ethyl. Okay, again, we're going to put in our dots. Okay. So I'm going to say this is the C-O that we keep. So these two carbons here, okay, are going to be these two carbons there. So what we need to do is we need to add a 2-carbon piece and this 6-carbon piece. 1, 2, 3, 4, 5, 6. And so we need to go through that process, that iterative process of taking away the hydrogens. Okay? So sodium methoxide, right, to make O-ethyl, hydrogens, right? So that's gonna rip away the hydrogens, put them up here on the carbon. Right? And then let's say we put in the ethyl group. So so then this attacks here, kicks that away. And so you end up with but remember there's still a hydrogen here, right? Didn't do anything with that hydrogen. So we're going to go through this process again. So sodium methoxide. Right? This is going to grab that hydrogen, put those electrons up there, so you end up with right? So now we need to add a 1, 2, 3, 4, 5, 6 carbon piece. Okay, so 1, 2, 3, 4, 5, 6, right? And then a bromine here. And so this is going to attack there, keep that away, and so you're going to end up with and then 1, 2, 3, 4, 5, 6, right? And then when you go through this decarboxylation process, so first time you throw in sodium hydroxide, and then you put in acid and heat, okay? Remember, you get rid of one of the esters, and then this side becomes an OH. Okay, so that goes there. Good luck.